stuff that, like, if I tell you that this is a multiplication rule problem, you're not going to have difficulty carrying out the multiplication. It's recognizing that it's a multiplication rule problem, recognizing that it's addition rule, and is it some sort of distribution? Just going through all the things you've learned about probability and trying to kind of pin it down onto a particular topic, because once you know what topic it is, it's easy enough to actually carry out the process. All right, so this one is the at least one rule, I guess. I don't know that anybody has a name for it, but I'm sure that's probably what would come up if you Googled it. So we'll call it the at least one rule. All right, so at least you have an idea of what I'm talking about when I reference it. All right. And just a reminder, kind of feels like I probably shouldn't have to put this in the notes, but at least one means one or more. All right. So it wouldn't be there if it wasn't an issue in the past. So the whole at least, at most, I mean, more than, less than, that's easy enough. But for some reason, people will get those the at least stuff backwards, at least, at most. All right. Now, in the first example, it says find the probability of tossing at least one head in two tosses of a fair coin. So I'm just going to take you through. I'll only do it for this problem. I'll take you through the longer way of doing it. It's not long, though. It's still quick based off of the framework of the problem, but this would be the more brute force approach. So if you're tossing at least one head in two tosses of a fair coin, we have coin one and coin two. For coin one, your possibilities are heads or tails. And then depending on which outcome that was, so you're at the fork in a road, you decided heads, for example. When you get to the next fork in the road, it's going to be essentially the same decision. Is it heads or tails? So I would account for both possibilities. All right. So like a decision tree, but also like branching off. All right. We look at all the possibilities. Like I just caught up with Loki, so like that's a pretty good example. At any moment, a decision can be made, and it creates a branching off point. And so you could have infinite possibilities if you try to look at this in a real world context, like a person living throughout one day. Right? It would be an infinitely more complex tree than what we have here. But in this experiment of just flipping a coin twice, it has to boil down to be one of these possibilities. All right. So if I want to find the probability of tossing at least one heads, I could go down the heads pathway. I have at least one head automatically just by going down this pathway, but I'll follow to a conclusion. So we have two possible outcomes if I just follow that branch. And if I follow the other branch to tails, I don't have at least one head yet. And if I go down here, I still won't have at least one head, so I'd have to go over here following that branch. 3 out of the 4 branches gets me at least one heads, right? So, and not overly difficult to do, even if I did the sample space, HH, HT, TH, TT. Like look at each possible pairing. If it doesn't have an H in it, we're not going to consider it, all right? But then you get to the problem of, okay, what if I'm flipping the coin 10 times? What if I'm rolling a die 7 times? Obviously not the kind of thing that you'd want to draw a tree diagram for. So what we use is the probability of at least one heads is equal to 1 minus the probability of no heads. All right, handwriting went off the rails there. All right, 1 minus the probability of no heads and 2 flips of a coin. All right. Now, when you flip the coin, so coin, I'll say 2 coin flips. The distribution of possible outcomes right? So I'll say possible outcomes is that I could get no heads, one head, or two heads. Those are my possible outcomes when I flip a coin twice. All right. So what we're doing here, if we look at this as the collection of possible outcomes, a complete collection, then our solution has to be somewhere in the probability of finding no heads, one heads, or two heads. So the sum of those probabilities is going to be equal to 1. So, and this is way more than the problem requires. I'm just getting the theory across. So what this is saying is I have the probability of no heads. I'll say 0 heads. Probability of getting exactly 1 head. Probability of getting exactly 2 heads. If I add those up, the result should be equal to 1. All right. This part of it here, this part here, is at least 1 heads. Right? So you see that the only probability that's been excluded is the probability of getting no heads. So if I take whatever this probability is and subtract it from 1, just algebraically, that's going to give me the probability of at least 1. So that's where this rule comes from. The idea that we're excluding the one instance where we don't have or heads in any capacity. Like I flip a coin 1,000 times. It is technically possible, mathematically possible, that you flip the coin 1,000 times, all of them to be heads or all of them to be tails, but odds are it's going to be some mixture. Right? So we find the one instance for the probability that we don't want, subtract it from 1, and we'll find the probability of the thing that we do want. Right, so no heads means tails and tails. They're independent, so I don't have to worry about that given stuff. Flip a coin 1,000 times. On the 1,001st time, you still can either get a heads or tails, 1 and 2 probability for either one of them. All right, so this is just straight multiplication. This process is doable with dependent events. It's just more complicated, but we'll get to it. All right, probability of tails is 1/2, 1/2. All right, it's happening twice. I could write that as 1/2 to the second power, or I could just do the operation, pop it into a calculator. I'm writing it this way in particular because we're going to get to, in the next problem, we're going to have to find the probability of at least 1 heads and 3 tosses. So that power is going to come into play. Regardless, I'm going to get 3 out of 4. All right. For the next example, I mean, I'm really going to write a lot of the same stuff. I'm not going to do the tree diagram though, but this relationship is still going to be true. Actually, let me just steal all of this stuff and edit it. All right. So no heads, depending on how many times the coin's been flipped, that could mean tails and tails. It could mean tails and tails and tails and tails and tails. I mean, it can keep going on and on and on. So in this case, because it's 3 tosses of a coin, no heads means tails and tails and tails. Still independent, so still multiplying by a probability of tails, which is 1/2, which makes this a power of 3. All right, 1/2 to the third power is 1/8. 1 minus 1/8, 7/8. If I drew out the tree diagram for this, all but one of them would have had a heads in it somewhere. The only instance where it wouldn't would have been tails, tails, tails. 1 instance out of 8 possible outcomes. All right, and that's one of the reasons why I talked about sample size, wrong unit, sample space size 2 days ago, whenever it was. But it was the one where we had those tables, and it was like if you flip the coin 30 times or 2 times or whatever, how many outcomes would you have? That was for something like this, because if I flip a coin 3 times, I should have a total of 8 outcomes, right? One of which is the one I don't want. one of which, everything else is the stuff that I do want.
Does this, I guess, identity or rule work with like things with like multiple outcomes, more than two, like a deck of cards?
Yes, if there is replacement, then this form. So they have to be independent. I'm going to show you a different technique for when the events are dependent.
Okay.
But for now, yeah. All right. So yeah. So for the last one, last one related to a coin. Probability, at least one. Oops. Is equal to 1 minus. I could say probability of no heads. 1 minus probability tail, tail, tails, 1 half, 1 half, 1 half, 37 times, of course. Or I could just, kind of cut to the chase here. The only thing that differed from the first example to the second one was the power. So it's really 1 minus 1 half raised to the 37th power. All right. Now, the calculator, when you deal with extreme powers, the calculator sometimes has difficulty with that. So I'm going to pop it in and see what I get. I may have to do some rounding. So in this case, it's really kind of strange. I don't love how it happens like this. I'd rather have the scientific notation than for it to say it's about 1. Like, yeah, it's about 1, but like it's not 1. Calculator doesn't know we're doing probability right now. So when it comes back with a 1, it's trying to tell you, specifically in this case with the approximate symbol, that it's very, very close to 1. We don't have the capacity to really represent it as anything other than 1, but it's kind of conflicting because then when you hit OK on the number 1, it actually reports a better approximation of the decimal. All right. So we really don't want to write 1 unless it's a certainty. This is not a certainty. It's damn near a certainty, but it's not exactly a certainty. So I'm going to say one of two things. Either I'm going to write that disgusting fraction or I'm going to write that disgusting decimal. All right? I'll do both. Just take the union of my two possibilities. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 nines? I suppose I could have just stopped at a 3 here if I wanted to round it, but it's just 2 additional characters, so it's fine. All right. So then using what we just talked about, I'll write a kind of a generalized form of this. Probability of at least 1. 1 minus the probability of success raised to the nth power. So semicolon, P is probability of success, N is the number of trials. N could be really a bunch of different possibilities, but in this case, the number of trials. So for this problem, apologies, probability of failure. Right, because we're subtracting off the probability of the thing we don't want. Right, it just so happened in the last problem, the probability of the thing we wanted and the thing we didn't want were the same. But in the case of rolling a die, not so. At least 1 4, the probability of getting a 4 is 1 out of 6. The probability of not getting a 4 is 5 out of 6. Raised to the 6th power. So it's another one of those cases where we're going to pop it in the calculator, see what comes out, and then make a decision on how we want to write our answer. Power of 6 isn't terribly large, though, so I think we're going to be all right. Yeah, so here it gives us 31,031 over 46656, which is about 0.665. All right. So, like in the end, you sort of look at it and say, well, all right, we got yet another rule we got to remember. But that's why I showed you the tree diagram approach early on, because hopefully it's a more intuitive thing where you're not actually memorizing this particular formula, but you have an idea of how the solution works. All right, it's like, all right, figure out the probability of the thing I don't want, subtract it from 1. It's the definition of a complement. All right. So if I tell you the probability it's going to rain tomorrow is 70%, and I say what's the probability it's not going to rain, you just do a quick subtraction, you get 30%. Right? So you're subtracting from 1. If you have that idea in mind, then all you have to do is worry about what you're subtracting from 1. All right. The next page we have contingency tables. I don't know why I retitled it, because this is still part of the lesson of complements and conditional probabilities. So this is actually related to conditional, probabilities. All right, so that's our if-then stuff. Should be an equal sign if you didn't already get that. All right, so the probability of B given A is equal to the probability of A and B divided by the probability of A. Right. Notation-wise, and again, I mentioned this, I'm losing track of days, but I wanted these to be using the proper notation. I typed the word and previously, but I would like to change this to the actual and symbol. So if you notice that going through the packet, even the ones I don't point out, and you want to get some typo bonus for that, just send me an email, because it happens fairly frequently. It's just well, actually, to be fair, at that point, I didn't know that I could type the union and intersection symbols. So once I learned how to do that, then I tried to make the effort to change it, and I just missed a few along the way. So what this is telling us, among other things, is if I have a standalone problem, what's the probability of getting an outcome given that something has already happened? If I know the probability of them happening concurrently, and I know the probability of the first event, then I can figure out the probability of the second event based on the fact that the first one has happened. And this is a simple form of something called Bayes' theorem, which we're going to get to actually over the next couple of days. So there's a lot going on with this one, but in terms of contingency tables, it's actually pretty easy to handle. So a contingency table, in this case, we're referencing a 2x4 table. It's 2 variables, all right? The first variable is some sort of decision, yes or no, and the second variable is your age group. Whenever you create a table comparing 2 variables and the counts associated with those 2 variables, then you're looking at what's called a contingency table, right? And this will actually be something that you can do with your daily data, because like for mine, for example, if I'm doing pollen count, I might want to do pollen count by season, so I could find the number of or the pollen count in the range of like 0 to 4 and compare that with the season and just count up each instance in which I have a value of from 0 to 4. You don't necessarily know what the scale is, but so far I've only seen up to like mid-11s as the high pollen count and 0.1 as the lowest. So I could break it up in intervals and then compare those intervals by season. I'll do that probably today, and I'll show you tomorrow what I'm talking about, because like hand waving doesn't really do it justice. But it would end up being a table like this, and I could use my knowledge of probabilities, and then later on a chi-square test to determine whether or not there's a relationship between those variables, right? So in this case, yes or no. What's the topic here? Oh, whether you're going to go on a roller coaster. All right. So monster loop, very terrifying roller coaster. Are you more likely when you're younger to go on the terrifying roller coaster, or older, or is there some sort of like happy medium? That's one of the things that you can investigate. What we need to do anytime we're given a contingency table, if they didn't include the totals, we have to put them in. It just makes life easier. So it's not like we have to, it's like we want to. All right, so just running through, grabbing the totals. 32, 40, 54, 19, 31. Oh, is this the one? Hold on. 19, 31, 36, 32, 40, 54. I think they only add up to 90. 51. So, yeah. So I knew there was a typo in here. That should be 90 randomly selected people. All right. So the first example, or first question, I guess, find the probability of yes, given that the ages are 16 to 25. Just like I do with pretty much everything else, I'll show you the longer way of doing it just to get the theory across, and then I'll show you a nice shortcut. All right, so this is my B, and this is my A. So if I'm following the rule, probability of B given A is equal to the probability of A and B over the probability of A. All right, so just rephrasing this formula here. All right, so that's the probability. Let me use an arrow here. Yes, given 16 to 25 would be equal to the probability of being in the 16 to 25 interval and yes over the probability of yes. 16 to 25. All right. So going to the table, I would say the setup is probably the more challenging part to this, because when you go to the table, it's pretty easy to pick this stuff out. 16 to 25 and yes, that would be this value here. All right, that's the one that's the intersection. That's the one that coincides for the yes group and the 16 to 25 group. So 23 over my grand total of 90 is going to be my numerator. And then the probability of getting 16 to 25, just in general, that's any of these 34 people. So they're both over 90. The 90s cancel. You're left with 23 over 34. All right. And so that kind of leads into the shortcut, because if the 90 is irrelevant, the only two relevant values are the ones I highlighted. Why not just put one over the other immediately? All right. And so the way I kind of look at this is whatever is the given, we only consider that and really essentially just eliminate everything else. So my given here is 16 to 25. So that's this group here. The first, I lost my 34 there. The first value, it corresponds to the yes. The second one corresponds to the no. So if I'm looking for only in the given 16 to 25 interval, the probability of yes, I would just have to figure out the number of yeses and the total for that restricted interval. And then that would be it. So for the second one, it says find the probability of no given that you're in the 16 to 35 interval. So I need my denominator. It's a total of 20 individuals in that group, and only 12 of them are no's. or 12 of them are no's. So that's it. We don't have to do anything else beyond that, right? The next one, just kind of go the other way. For the next one, the given is no. So this is my given. And from this, I'm looking for the probability of being in the 16 to 35 group. So that's 12 individuals out of the 36 that make up the category of no. All right. And then the last one talks about independence. I think, yeah, I guess we could do it. When they ask you to determine if there's independence, what they're asking you to do is take essentially the formula. Probability of B given A is equal to the probability of A and B over the probability of A. And really just alter the formula so that it's solved for probability of A and B, which we actually had on a previous page. It's probability of A times, and actually on the top of this page if I'm not mistaken. So probability of A times the probability of B given A. Right? So this is the general multiplication rule. If the probability of B given A is equal to the probability of B, so essentially this part here, if that was really just the probability of B under ordinary circumstances, then A and B are independent. All right, so basically everything we've done on this page is some variation of the general multiplication rule. I'll just shrink and zoom in, hold on. So if I could demonstrate this for whatever variables I'm interested in, then I will have established that A and B are independent of one another. So they're saying find the probability, or well, they didn't say directly find the probability, but we're going to find the probability that yes and no is independent from age. So what I'll do is I'll grab a particular age group and I'll grab yes or no, it doesn't matter. If I show it for one and it turns out it's dependent, then I'm done. If it's independent, then I'd have to keep going. But I'm just going to, off the top here, say the probability of yes given you're in the 16, I'll do 8 to 15 interval. Haven't done that yet. So I want to know if that's equal to just the probability of yes. All right. So I'd evaluate each one separately. So my given is yes. Let me just get rid of this highlight. Just put it there for a minute. I'll actually make use of it here. Oh no, my given is 18 to whatever. So in my 8 to 15 interval, the probability of getting a yes, right? So that would be 9 out of the 17 in that interval. And then I would just want to compare that to the probability of getting a yes overall. This is the number of yeses overall, right? So that's up over here. Number of yeses overall and number surveyed in total, 54 out of 90. All right, so I would just check. I mean, sometimes it's obvious when you look at it, and sometimes you just want to get the decimal value. All right, so 54 over 90. So we're around 0.5 for one of them and around 0.6 for the other. So these are not equal. And because of that, so therefore, yes, no is dependent on age. All right. So the conclusion's kind of weird. So I'm saying if they were equal, the two events would be independent of one another. So if this ended up being an equal sign, then I would say the two variables are independent. Turned out they're not equal, so they're not independent, meaning they are dependent. 18 are red, 6 are trucks, 2 are both. Suppose a randomly selected vehicle. Oh, actually, that's weird. Typo. Determine the probability that it's a truck given that it's a red vehicle. All right. So I'm going to make the table here, and our possibilities are really truck or not a truck, red or not red. So I'll say truck, not truck, total, red, not red, total. And again, we're looking for the probability of truck given red. Abbreviations are fine as long as it's obvious what the abbreviation is representing. So we have a total of 40 vehicles. So that's my grand total. 18 are red, 6 are trucks, 2 are both. All right, so we know what the 2 represents. That's the instances of red trucks. All right. Out of the 18 accounts for all the red vehicles, but we know 2 are red trucks, so I would remove 1 from the 18 to account for the instances where we know it's red but not a truck. So I'd have 16 there, and it totals out to 18 red vehicles. All right, just like there are 6 trucks. All right, so the total for my trucks should be 6. 2 of them are red. The other 4 must not be red. And then you can kind of just work the table without having to think about it too much, because these 2 numbers have to add to 40, so it's got to be 34. These 2 numbers have to add to 34, so it's going to be, what is that, 18? Oh, wait. Oh, so 22 and then 18, yeah. All right. 34. I'm just double checking. Yeah, so we have a whole lot that are not red and they're not trucks. So it ends up not being the case that they care about that, but you never really know. So you make the entire table. I guess if you're doing it on an assessment, you'll make as much of the table as necessary to answer the question, but just be prepared to make the entire table. So the condition here is that it's red vehicles. From the reds, I'm looking for trucks. So 2 red trucks out of the 18 available vehicles, which if you want to simplify to 1/9, that's fine.